Good morning. It's really good to be here live at a conference. It seems weird that you're not on some kind of a Zoom or something else, right? So today, what I'm going to talk to you about is scaling machine learning in different ways in your organization, the components that you need to scale within your projects, and some of the things in the industry from more of an academic and education perspective where we have to marry together software engineering and machine learning. So the metaphor I'm going to be using today is basically taken from an old friend of mine, Grady Booch, who used to be a former colleague of mine. And when I said I'm going to use this, he said, wow, the metaphor still works. And I said, it absolutely does. So he would always say, hey, anybody can build a doghouse, but to build a skyscraper is very difficult. It requires engineering discipline. And he always talks about software-intensive systems. And so the second metaphor that I'm going to be talking to you about is the notion of tech debt. We're all encountering tech debt, day in, day out. And the notion of tech debt, though, is very focused on certain things in the engineering lifecycle. And what we usually know, looking back at a very important paper that came out at the time, The Hidden Tech Debt in Machine Learning Systems, which we all probably have read. And if not, you can grab that on the QR. I have these little QR codes for the papers that I reference today, so you can take a look at that. And it basically tells us that ML coding itself is important, but there's a whole lot more, and we'll go into detail around that. And the whole lot more becomes important, not just in an academic setting, but rather in the setting that is connected to industry. How do we get value from machine learning? A lot of times, AI and ML and statistics, used to call a lot of what is now with, under the guise of ML, pretty much statistics. And then we have deep neural networks, which is a little bit more than that, beyond just the basic statistics and statistical methods. And to do things in particular industries and activate use cases that are of value to your organization, we need to go beyond these small projects, and many of you, I'm sure, have. And somehow my voice is going up and down, and the volume is going up and down, such as the use cases, small use cases, big projects. But to derive value, this is one of the skyscraper ones, voice-wise. To derive business value, we need to really be able to scale across the organization and what we do. This means the personas, the interactions. A data scientist and a software engineer. So if they're coming from different backgrounds, if they're specialized from the get-go, and I do this, because I'm also a teacher, so I understand the differences between the two disciplines and the importance of bringing them together, and how a data scientist and a software engineer, if they're coming from different backgrounds, like not a software engineer who became what is now called a data scientist like me, but someone who's versed in data science or versed in software engineering, they don't quite get along that well, because they have different processes and different ways in which they function, and we need to bring that together. So that's the scaling of skill sets. And then there are components within the life cycle that are super important to realize. And this allows us to mature the organization in terms of deriving greater business value outcomes from these machine learning use cases. And so part of that paper, I'm just going to use that kind of as a backdrop, is the function of scaling just the model. Just let's focus over-index on the model itself. And so large language models, we have a ton of them that have come out, GPT-3, more recently, the Pathways language models from Google Research, and Lambda for conversational systems, Gopher from DeepMind, and Chinchilla, another variation of Gopher that we talked about. In one of these, Minerva was a language model that basically achieved a very high score in mathematics, in being able to perform computational mathematics in the math benchmark. And it increased the state of the art by like 43%, something wild. And it's built on the Pathways language model, which is the 540 billion. Everybody's in a race for how much bigger and better their language models are, right? So that's, at this moment, maybe the next moment it's going to be a different model, but that's kind of the largest model. But that is kind of irrelevant. I'm being slightly facetious because we'll see that some of these models are sparse, these models are dense. There are a number of pre-trained models that have been employed as a result of using PaLM. Minerva is one of them for performing math computation. And there are a huge number of them. And there is a scaling factor. This is from OpenAI that is beyond what we're doing today, and it shows the scaling impact. It's like 7 times Moore's law that what is happening in terms of the computation required to build these language models and the benefits that are gained from that. So the reason we focus on large language models is that they have very good performance with few-shot learning. And it's not necessarily task-specific and doesn't necessarily pertain to just task-specific data collection or fine-tuning the model. They can be quote-unquote zero-shot. And the NLP tasks are a wide, especially for the Pathways language model, they have a huge variety of downstream use cases that can be employed. And then there's an order of magnitude reduction in the turnaround time and the cost to prototype new experiences with these. So, you know, in this case, there's instances of prompts. You give it a prompt, and there are multiple additional phases of the prompt, and then there's the deduction that the language model can do. So again, PaLM is the 540 billion parameter model. It's the state of the art currently. It's a decoder-only model, and there are various techniques that were employed in speeding up training, and it was basically using 2 cloud TPU v4 pods with about 6,000 chips with the Pathways architecture between them in order to scale the division of when you're dividing the data and having the gradients and having them sent back to a specific place. One of the things that was the upshot of this, a lot of people quote this, was the explanation factor, the explaining a joke. And so in this particular case, it's around an eloquent whale and their pods and TPUs. And the model response was the TPUs are a type of computer chip, and a pod is also a group of TPUs, but it's also a group of whales. And the joke is that the whale is able to communicate between 2 groups of whales. So it derives those types of architectures. Decoder-only architectures have a variety of different techniques that were employed here in the 8 billion, 62 billion, and 540 billion versions of this. And in fact, the 62 billion version of this performs way adequately, and the 540 billion one is very strong as well. The 62 billion version of it actually performs better than the next best model that's out there in the industry, which was very interesting. Some of the English language, tasks, in this case English language NLP tasks that have been previously employed by other models have been surpassed by PaLM. And we have some, basically the amount of GPU used is much higher. It goes up to between 46 and 57% of GPU usage as you perform the training. So this is a very powerful model in that sense. So, squeezing the last drop out of data, this is something from DeepMind where they basically trained a model called Chinchilla. Before they had a model called Gopher, they basically trained it about 4.6 times, with 4.6 times more data, and it created a much smaller model, and it got much better performance. So those are some indicators that training with a larger number of models and squeezing the last drop of data makes a lot of sense. So now we're going to focus on the surrounding things, not just the model itself and cool stuff that may be happening in the industry. And this is more than primarily the focus of what we're doing here. Okay, so in that paper, the hidden tech debts, there's an other section. A lot of people don't read that other section, I've noticed when I talk to them. And these are some areas of that other section. The data testing debt is super important because in software engineering systems, we test code a lot. In machine learning, we need to test at least as much the data because that's what we're giving it to train models. The next one, and I'm going to pause on this one slightly, is reproducibility debt. And this is the ability to rerun the experiments. And the problem with the reproducibility is that oftentimes there's data leakage that seems to occur. There was a paper that was written in July of this year, and this was from Princeton University. They talked about reproducibility and leakage. So they started categorizing a taxonomy of all the different types of leakages that are out there. I think this is one of the a main problem. That's why I'm kind of pointing it out. They analyzed like over 300 applications in the sciences and noticed that there was a very significant amount of errors in the papers pertaining to that training. And so, so obviously we all know that, train and test shouldn't be mixed, but it is in many cases. So that to watch out for, obviously. And then sometimes the features are a proxy for the outcome variable, and sometimes the distribution of the data that was used in training is different from the distribution of the data in testing. And one of the main things that they were focused on in this paper was the applications in the sciences, so that middle tier there. So in this particular case, as I said, there were like 300 papers they analyzed, and a significant amount of them had these taxonomy errors involved. And so they were basically talking about, okay, let's do something about this. And they introduced something called model info sheets. But the precursor to these model info sheets was from the University of Toronto. And in that, they were using a technique called model cards. And so what model cards does is it basically lists out the details of the model, what the intended use is, what are the factors, the metrics, the evaluation data, the training data, quantitative analyses that are done, ethical considerations, caveats and recommendations. And so with this model card this was the reason why the other researchers were able to actually investigate these other 300 programs and found them not to be conformant. They were having some kind of data leakage and the reproducibility problem. So they introduced, so this model card is basically showing a whole bunch of, and you'll find it there on the University of Toronto website. They show different false positives, false discovery rates, and false omission rates, which are, I think, interesting to take a look at. So back to Princeton, those guys, inspired by the model cards, are now talking about model info sheets. And basically, they're talking about a clean separation between train and test. It sounds obvious. We all know this. It's the basic thing, train, test, split, all that. But in fact, in the actual research, when it comes down to it, this is not carried through, not in nefarious ways, in inadvertent ways. So either the model uses some features that are not quite legitimate, or they're representative of the outcome. And again, I talked about the distribution of the training test set, and at inference, by the way, when you need to monitor the model to retrain it. The next one is the process debt, where various different configurations lead to varying types of models and systems. And so it's super important to visualize the data, its flow, and the blockage of data across the pipeline, so that the process of building these large number of models can be detected if there are issues with them. So one of the things that has been very helpful is to try to, in the industry, industrial strength systems, to try to look at, different levels of, if you will, maturity, adoption, so teams can actually reproduce results in an effective way. One of them is to kind of go through what each stage each team is in the organization, such as, for example, having very clear goals for the use cases in terms of the ML aspects of the use cases, applying the processes, the ML process itself, that are consistent across phases, and then making sure there's some kind of a documented reference for what they're doing in each of these phases, and automating those tasks, and then measuring at each stage what the bottlenecks are, and then improving on it. In order to scale, from small projects I do on, my little, corner of the world, or someone else, in their little corner of the world, in order to scale for the entire organization, these are the elements that become super important. And then there's this cultural, quote unquote, cultural debt, where we talked about the difference in the personas and how these personas are interacting with each other in a way that is different. So creating a culture where deleting features, reducing complexity, pulling down tech debt, having constant monitoring and understanding the data as it's flowing from one phase to another, and creating those feedback loops becomes super important. So these personas in the ML lifecycle are significant. Not enough attention is paid to what each does across the lifecycle and how they're handed off. This allows us from scaling our machine learning programs across multiple projects and programs in the various industries. Another fun thing that Grady Booch was talking about a while back was, this whole Godzilla, in the science fiction kind of story, right? So they've grown so big that they would be crushed. They can't be so big. So in the same way, he was saying that you can't really just incrementally build a system from something very small. You just can't do that. It'll be crushed under its own weight. So the paradigm, I'm going to build something small and then just add to it, eventually getting that skyscraper from the doghouse, that's not going to scale. That's not how we scale. A lot of times that may be how some teams are hoping they scale, by using that metaphor. So the scaling the architecture of machine learning systems requires a combination of software engineering best practices and machine learning best practices. Okay, what are they? Well, I don't have time to go into it, but I'll mention one, which is testing. It is super different in software engineering and machine learning. How we do testing is completely different. And marrying those two together, or at least aligning them, is going to be super important to the success of a project that you're interacting on. So, for example, you have different types of activity in the machine learning lifecycle. You have your data analysis, your training and deployment, and all that kind of stuff. And in software engineering, you have the notion of tiers, you have the notion of middleware, you have the notion of security and reliability and functionality that you need to be implementing. These are in almost two different worlds, and when you talk to people at this research was talking about in terms of different levels of expertise they have across the life cycle, there are significant problems when it comes to data availability in integrating AI into larger systems. The dichotomy between software engineering and data science machine learning becomes very, very apparent. And one of the reasons is because they do very different activities. The ones in green here are more the ML activities. The ones in white, or the lighter colors, essentially, are more of the software engineering activities. And very often there's not very much overlap. The CI/CD is one example, one good example where there is overlap. So that's a second area of convergence. Testing, CI/CD, those two areas of convergence. And then, of course, data preparation is going to be significantly important. So unifying these two types of activities is going to be super important. And so in order to scale your model, Does that mean it's over, or that means like it's 1 minute left? It dimmed, so it's like 10 minutes. Okay, thank God. I can slow down just a little bit. It's like on YouTube when you slow the thing down. It was like on 1.5, and then when it's on 1, it's like this person's talking very slow. It's relative. So next point is scaling the components themselves. What are the components you actually need? Yes, one of the important things is a human component, the personas and how they interact. The second one are the actual, if you will, software-ish kind of components that you need across the life cycle. So as you intend to mature across the life cycle, at the bottom there are various sets of capabilities. I know the Google version, so I've put some of those names there, and I've put some things in parentheses of what the equivalents are, like I said, BigQuery is a data warehouse, etc. So the point here is that there are various technologies across this digital innovation spectrum that can be applicable in a company, in a domain in the industry, or a portfolio of companies. And each of those vertical areas could be super applicable to one area, one product, one component, and it may be enough for that particular line of business. Marketing, for example, may just want a data warehouse and they don't care about anything else, and visualization. Engineering may want, hey, I need custom models, I need ML ops, and I need IoT devices, and that's all I need. But in order to mature across the organization, to be able to scale projects across, you need to be, you, the people who are interested in scaling ML, need to be able to scale across this spectrum. And in order to do so, we talked about some of the things in terms of process and people. These are the things themselves, the components, the ingredients that we have to be watchful for. So one is the data lake and the feature store. Data lake, everybody knows about a data lake. We always dump garbage in the data lake, which we shouldn't. We need to have the governance process around it to clean it up in a periodic basis, and then prepare the data in a feature store of sorts. So it's a gold standard across use cases within the organization. The experiment is a fundamental construct in machine learning. Actually, we're not training models. We're running experiments. Let's come out and say it very clearly. We are running experiments. It's like a lab. We're taking this piece of data, modifying it in a certain way. Did this colleague of mine change the data, or was it this other colleague of mine who cleaned up the data? Or was it the one I did last week? So that lineage, the provenance of data is super, super critical. So you put a gold standard in the feature store, it becomes extremely important to be able to leverage that across the organization. Now, data and model governance require things like a model registry and being able to access metadata from the model. What's the version? What data was it trained on? What tests were run on it? Where was it deployed? What are the current distributions? When you're monitoring it, what feedback do we have relative to the distribution of the incoming data and the actual inference that was implemented using a different training distribution? What's the delta between those? So that's your registry, your experiments, explainability, and data governance, and then, of course, pipelines. But if you go into, actually it's mentioned that tech debt paper, where if you have pipelines that are too convoluted, it's going to defeat the purpose. So smaller pipelines that you can put together makes more sense in most occasions. So these are basically the key ingredients. And again, as I mentioned, in order to marry together machine learning and software engineering, there are a couple of areas that are low-hanging fruit. I'm sure there are others. Data prep, the actual, someone is approaching, so it's like, okay, I'm kidding. I'm kidding. Data prep, testing, and CI/CD are three of those areas. And so when you have those, that data about the ML models and their metadata and the data that was trained and tested in the feedback loop from monitoring, you can put them in the registry and look at the metadata and understand how it needs to be changed so that you can create an efficient but also responsible AI ML set of models that are explainable, to a degree, to the degree that is feasible based on the models that you're using. A lot of these very dense large language models, we have no clue what is happening in them. In some other cases, we do, and we have methods to check for explainability. And then, again, that governance requires the feature store, model registry, and the metadata for the experiments. Those are critical things, control points for your governance around ML, and the explainability that needs to be at the basis of ML. I don't know how to go back on this thing. Someone wanted to take a picture of this one. Yeah, here you go. So these three elements are critically important choke points for the actual governance model. They are mechanisms that you can leverage. And then finally, we saw this. Remember that picture in the brain. Get the data house in order, track those experiments, explain those models, create those small automated pipelines, put them in a registry with the metadata. So the experiments are the fundamental concept, not my data, not the model, but the experiment, which brings everything together. And then I will leave you with these images, hopefully positive images. Right components, right process, the model cards, integrating software engineering and ML so that you can build that skyscraper and architect for the right size. So that is all I have to say for today. Any questions?
Thank you. Thank you.
Can you hear me? Oh, okay. Thank you very much for the great talk. I'm Vinod Charyam. I'm a senior lead data scientist from Innova. We're a fintech company in Chicago. While you were going through the section, especially on like the model info sheets and then trying to find out how the models fit together, I couldn't help myself thinking about, drawing an analogy from engineering, right? So we build giant jumbo jets with like millions of parts, and then they all need to be validated, all the connections need to be checked, and the engineering world has solved that problem by using two things, right? So one is they represent all those designs using what's called SysML, the systems modeling language. It's an XML-based language. And then they use automated validation codes to kind of, that's how things, Boeing and the other companies actually do these things, right? And when I look at the machine learning world, we have PMML, right? The predictive model markup language to kind of capture the model structures. We have fairly advanced data lineage kind of techniques, right? So data dictionaries and trying to map these things. So I'm wondering, why can't we use something similar that we used to solve it in engineering world into this world, like, represent these architectures using an appropriate structured, semi-structured language, and then use automation to figure out, all those errors and, catch those things. So is there some underlying theoretical challenge with that, or is it more of, is there more of an implementation thing? Like, I'd be curious to hear your thoughts.
Absolutely, great point. From the perspective of this talk, I'll just point to one angle of that, which is the tech debt problem, where we accrue tech debt from various angles because we try to cut corners for whatever reasons, and we don't apply those principles. So the effort here was to bring the software-intensive engineering discipline, as you suggested, to machine learning, using a variety of very specific techniques that we're describing, least of which could be monitoring, data collection, and then reigniting a pipeline or some segment of a pipeline in order to do so. That monitoring becomes critically important. Having the data in a feature store to begin with is critical. So at each of these stages, that systematic know-how of what to do at that stage for that engineering discipline is essentially what we need to do. Yes.
Okay. So what's missing is that the way discipline about that discipline. Okay, yes. Got it. Okay.
We have all the tools.
Okay.
We just need to put them together, and we're always in a hurry to get stuff out the door.
Yes.
So cut back a bit on that, automate it so that it becomes faster, and marry the disciplines together. So, because what's happening is that we have communication barriers between roles and personas, between techniques, and between phases of the life cycle. The objective is to remove those barriers to some degree so that we can accelerate across them. This is a supply chain, so it's all about speed across. Yes.
Thank you very much. Yes.
Great, thank you. Any other questions? No? Thank you very much, Dr. Arsanjani. Appreciate it.